Hey, good morning, everybody. Thank you for joining us on our RACO webinar today. Our topic today is going to be 5 key things to know about real-time aerosol measurement instruments. And leading us today is Scott Norman from TSI. Scott's been kind enough to join us before to host some webinars in the past. We appreciate that. For those of you who don't know Scott, Scott's the product specialist for the health and safety product line. And most of his responsibilities are a lot of product training, application support for many of the photometers that TSI manufactures. Scott's a certified industrial hygienist, and he's also a certified safety professional, and has been in the industry for about 20 years. So we thank him for his time. Couple of housekeeping items. We will be doing a recording of this webinar, so if you jumped in late or you wanted to share it with somebody, that will be available to you. Recording will be available at our training page, which is raco.com /training or /training. If you have any questions at all during the presentation, the presentation itself will probably be 30-35 minutes, and then we'll spend some time with questions at the end. You should have a little pane at the right-hand side that says questions. So if anything pops into your head while the presentation's going on, please enter it there, and we will address it. So without further ado, I'm going to pass it over to Scott, and
Great, thanks,
go
Tom.
from there. Thanks a lot, Scott.
Thanks. Good morning, everyone. I still have a hard time talking to a TV screen. I talk to myself a lot driving, but standing in the office, it's weird to do that. So I should have put a couple polling questions out there just to make sure you can hear me and get some input, find out who we're talking to. So yeah, the title, 5 things about 5 key things about real-time aerosol monitoring instruments. I want you to leave with 5 key points in your notes you can kind of keep in mind, but there's a lot more than 5. So I'll be throwing some other stuff at you, and I had a hard time limiting my slides down, so I'm going to go fast here and hopefully get through them all. But just to put in perspective, just to start out, how do you measure aerosols, and why do we measure this way? So I asked that to a group of hygienists, and they just kind of sat there, right after lunch, and they were like, it was the carbo loading kicking in. So we measure aerosols gravimetrically, usually, because that's what our metrics are based on. Most of our aerosol metrics are mass. It's milligrams per cubic meter. It's micrograms per cubic meter for silica, for volume fume, for any other aerosol dust you can think of. So that's why traditionally we've done a lot of gravimetric measuring, I think. So there's other instruments we have for measuring other exposures in real time, and those instruments are available for aerosol and dust as well. So these are some things I didn't always know about when I was in the field. Either I missed a day of class, or we didn't have the right information available when I went to school. We didn't have all the tools available for sure once the system programs. But so my goal today is just help you understand the value of real-time aerosol instruments. Some of these things you may not have thought of using them this way before, but it's really you can be a hero at the end of the day if you're collecting some extra information, extra data you didn't have before. And it's all about collecting data to make a better decision about protecting someone's health. So industrial hygiene, exposure monitoring, we have various numbers of tools, and now here's these tools for measuring aerosols in real time. The better information you have, the better decisions you can make. So I'm going to start talking about what are aerosols and how do we measure them, and then I have an overview of some of those real-time aerosol instruments. And then the real key points is how these light scattering photometric instruments work. I'm going to focus down on the photometric instruments like the dust track. Talk about the strengths and limitations of those, and then what's the value of that real-time log data. So you'll see the importance of getting information right now. I have some case studies to talk about, an application example, and one of those applications is really demonstrates a clear return on investment. We'll see at the end here this person was a hero at the end of the day because they used some real-time measurement and were able to find out the cause of the problem. So that's what we're going to jump into. So just after that, I'll ramble about 30 minutes here. We'll have some time for question and answer. And like Tom mentioned, this will be recorded. You can get at it later for future follow-up. And my contact information is on the end if you want to follow me for other questions here. So aerosols, dust. Obviously, dust is an aerosol. When we think of dust, that tends to be kind of limiting in what an aerosol is. But obviously, a lot of activities, industry, agriculture, construction, mining, even woodworking you're generating dust. So dust is definitely an aerosol. But aerosols are so much more. So we use the term aerosol that kind of opens our mind, our thinking patterns, like, okay, there's other stuff out there, kind of like welding fume. So welding fume is definitely an aerosol. Those fumes are small metal particles that are aerosolized from the heating process. So you don't limit aerosols just to dust. Include fume, and then think mist as well. So you have metal cutting operations, like in a machine shop. You might be generating some oil mist. It might be some mist coming off the tools. And obviously smoke. Smoke is present in a lot of industries and activities, not just by mistake, but intentionally. And then, a lot of industries have multiple sources of aerosols. So a picture of a guy at a foundry here. Foundries are nasty for health exposure. There's silicate dust, you have smoke aerosol, you have metal fume aerosol. There's a whole variety of stuff going on, not to mention heat and molten metal and heavy stuff, and there's just a lot of hazards there. So, we're talking aerosols. You can't talk about aerosols without mentioning size. The size is important because that determines where that aerosol ends up in your lung. So our lungs have some protective mechanisms, keeps the big stuff out, but the little stuff goes in deep. So this graphic we've shown before, just try to give you the scale of how small some of these things are. So a grain of sand is 90 to 100 microns or micrometers in diameter. So those are boulders. Those are big, huge boulders in the aerosol world. That long pole there is representative of a shaft of human hair. So about 50 to 70 microns in diameter, depending on what shampoo you use and how old you are, I suppose. So those are big. So the blue balls are getting down to what we're thinking of aerosols. So those blue balls represent PM10, it's particulate matter 10, and that's 10 micron diameter particulate matter. So if you're measuring the PM10 for outdoor air pollution, those are the sizes of aerosols you're looking at. So we look at this graphic, there's 5 of those spheres of PM10 will fit into one follicle hair. And then each of those blue balls has 4 red balls in it, and that's PM2.5. So PM10 is stuff like pollen and mold. PM2.5, those are the ultrafines. That's getting into combustion byproducts, metal fume, and those are getting pretty small. So for occupational exposure, we're usually concerned with respirable, which is the same as PM4 basically. So they'd be a little bit bigger than the red balls. But it's interesting to show that the red balls, there's 4 of them inside the blue balls. There's 5 blue balls inside the diameter of a hair, and these are really small. We can't see them. So the size affects where it goes in your body. So this graphic shows the big stuff, greater than 10, really doesn't travel very far into your lungs. It's going to get snagged in your nose and your mouth. That's the stuff you blow your nose at the end of the day after raking leaves. You see the black stuff in the Kleenex. It's 10 to 2.5 will get down into your tracheobronchial region. That gets into the lung passageways. And it's the respirable and smaller, 4 and smaller than the PM2.5. That gets down to that alveolar region, which is the end of your air exchange. Those are, I've heard it explained like little tiny water balloons that as you breathe in and out, they expand, contract. It's just basically a cell membrane thick, that tissue down there, and the oxygen comes in and carbon dioxide goes out. And when you have a lot of aerosol collecting down there, that little stuff that gets way down in there, there's no defenses for the lungs to chase that stuff out. So it basically floods red blood cells in there, trying to protect them, and then the red blood cells coagulate, and you kind of end up building up scar tissue. Now that air exchange doesn't happen very well. So then you have emphysema, you have lung disease, you have problems breathing. So that's kind of the bigger picture. And again, I'm kind of looking at junior high level some of this stuff. I work with a lot of PhDs, and I can't match with them on some of this aerosol physics stuff. But for our understanding, we'll look at how the size, the little stuff goes deep in your lungs. That's about all you need to know. So measuring aerosols, like I mentioned earlier, we use a gravimetric sample pump. I have a picture here of to sell a side pack pump at TSI. That product's been discontinued, but I don't have copyrights to use other people's competitors' pumps in their presentation, so I just keep our old one here. So we have a pump that pulls air through a tube. At the end of the tube, we put a filter cassette with a filter media on there, and we've hooked our filter cassette up to a flow meter, which we still sell as flow meters. So we're measuring the airflow to calibrate the pump, so how fast the pump moves, how much air comes in. We're going to run that over a set amount of time, so you can determine the exact volume of air that goes to that filter. We send that filter off to the laboratory. They're going to analyze it or weigh it, and we'll know how much mass of aerosol collected on that filter, and then we can determine our mass per unit volume of air. because that's where our exposure limits are based on, is mass per cubic meter of air, something like that. So that's not going to go away. Don't throw away your pumps. That's not going to go away. We still need to find out, this way if we're in OSHA compliance. But if you've done that, you send your stuff out and you wait a couple weeks for the data to come back, and it takes you about another week to get your data into your report and information back out to your employees. And I've done sampling about 3 weeks to a month later. I'm giving the results to the management team saying, well, yeah, 3 weeks ago this guy was overexposed. He should have had a respirator on. It's like, well, it's good to know that now. How come we didn't know it then? So how fast do you need the data? And so here's a picture I found from NASA. It's a picture from space of Lower Manhattan on September 12, 2001. So the day after the terrorist attack on the World Trade Center. And there's a visible aerosol cloud heading to the lower left there, you see. So that aerosol is smoke and dust particulate, and who knows what is in there. We hear about all these lung function issues the responders have, and even people living in that ground zero area. They were exposed to high levels of aerosols and ultrafines that day, and for following weeks. And we didn't have a good number on it. We didn't have a good metric around, should people be here or not. So, there are, EPA has monitoring stations, which is basically a gravimetric filter that they check every week, and they put a new filter out every week. So it takes a while for that data. And that's your long-term stuff as far as urban pollution goes. It's like, do we change the policy that requires different air permits for coal power plants? It's based on this long-term data. We're not getting the information fast enough to make a decision today like we need. And our emergency responders are kind of realizing that. 9/11 taught us a lot of things. And we talked to some emergency managers recently in New Jersey. They were talking to us. They're actually within view of the New York skyline, and they realized that, look, they're in a fire scene like this. The fire incident commander or the fire marshal is in charge of not only the people on the ground fighting the fire, but they're responsible for the community protection of the community as well. So they need to be able to answer if the governor calls and says, how far down when do we have to evacuate, or how do we shelter in place? What's that exposure level? They don't have aerosol instruments right now. They're looking at getting some that they can deploy. But their answer would be, we've measured with the instruments we have. There's no levels of concern with the instruments we have. Well, that's an easy way of saying we don't know what the aerosol levels are because we haven't measured the aerosols. We've measured oxygen levels, that's fine. Flammable gas levels, that's fine. Radiation levels, that's fine. They've measured these things, but they didn't have the tool to measure aerosols. So they're looking at getting something like the dust track they can deploy and get real-time information quickly to make a better decision. So the better information you have, the better decision you can make. So this measurement aerosols won't go away. You're still going to do this. Everything's gravimetric based. You need to know what people are exposed to. But there's a number of instruments we use on a regular basis that are real-time. We use all the time, don't even think about it. So if you're driving, here's one example, and you've ever been pulled over and gotten some feedback from a law enforcement officer, the first question they asked me this one time, do you know how fast you were driving? I'm like, oh, jeez. So they do that for, I don't know why they do that. They just see if, they're going to be honest and you lie. So if you answered, well, I've been driving for 15 minutes, and I've traveled about 30 miles, and I have about 80 more miles to go, and when I get there in 2 hours, I'll call you, and I'll tell you how long it took me to get there. We'll figure out how fast I was going. And that's not going to work. We have real-time instruments that tell you how fast you're going. Speedometer. Pilots use altimeters. That's important. They want to know right now how high the airplane is. Thermometers, scales for weight, noise dosimeters. We have a lot of instruments we use in real time. So there are instruments that we rely on a regular basis. We need that information now to make a better decision. So for aerosols, there are a number of instruments out there that can give you real-time or near real-time data. So this is a partial list. It's not representative of everything. The top couple, BAMs, TOMs, these are really used in that outdoor monitoring, the long-term EPA type stuff. What's your regional air pollution levels? Those are really your federal reference or equivalent methods for those. Piezoelectric microbalance is something similar. All three of those actually physically, there's a physical change in structure as the aerosol accumulates. They physically measure the mass through, beta attenuation or the oscillation changes, whatever. So then there's a couple others. There's particle sizers, differential mobility analyzers. So TSI makes some of those. These are the research instruments. So when they're doing studies, you read about the studies of, how many of this size particle was emitted from the tail end of a Volkswagen well, that's probably false because you read the wrong information if you saw the reports recently. But there's research instruments. These are in the lab. The instrument, a car will be mounted to a rack. It's running at a controlled, engine level, and there's exhaust hooked up to ventilation, and you're measuring particles coming out of that exhaust. So aerodynamic particle sizer will tell you exactly how many particles of what size you have. So they're expensive. They're research level stuff. They're not easy to use. The bottom three, integrated nephelometer, or I'll call it photometer, that's our dust track. Condensation particle counter, we have that technology in the P-Trak. Optical particle counter we have as well in handheld particle counters. I'm going to talk more about those because those are more about what the industrial hygienists will use. And then I'll dig a little deeper into how the photometer works. So we're talking field instruments, battery operated handheld. We can carry them into the field easy enough, turn them on, get some information. So we have the dust track. I showed a picture of our dust track here. There's a desktop dust track. We have a handheld version as well. The Aerosol 9000 series, 9306, that's an optical particle counter. That's going to count different sizes for how clean the clean room is. It's a little different application, not really an IH exposure instrument, but maybe used for indoor quality issues. And then the P-Trak. So our P-Trak is a condensation particle counter. So here's a good trivia question. If I had a poll thing, I'd do that again. What OSHA exposure limits are based on condensation particle counting? So number counts. And it's a trick question because there are none. So they're all based on mass. So the P-Trak doesn't measure anything compared to an OSHA reference, but it counts numbers of ultrafines. So it's an interesting tool to use for a certain thing. I'll show you an example of that in a couple minutes. So how these things work, dig in a little deeper here. The photometer, air comes in the top. This is kind of a cross section. Air is represented by these bubbles. Comes through an optical chamber. There's a laser beam, some kind of light source that's focused. And in this optical chamber, it's all dark, and there's a mirror at one side, and there's a photodetector on the other. So the photodetector is seeing light scattering off these, that laser beam as the aerosol comes through. So you hold a really bright flashlight up, next to your arm's length, put it straight up in the air as you stand by a campfire at night. That's similar, 90-degree light scatter, and you're seeing a bunch of dust and smoke and stuff going through that beam of that flashlight. Optical particle counter, again, is pulling air through a chamber, and the optics are a little different because an optical particle counter is literally counting the number of particles, and it's sorting how bright it is. The brightness will be associated with the size, so it's going to keep track of how many or how bright. So again, this is kind of the simplistic 5th grade version of it because I don't know technically how it really can do it. But there's different angles of measurement and the photodetector is a little bit different in this than in the photometer. So it's measuring particles and it's counting them by size and puts them in different bins. So it's not going to know there was exactly this many particles of exactly this size, but from this size range, from 1 micron to 4 microns, will give you a number. From 5 microns to 7, it gives you a number. And there's millions of numbers in some of these particle size ranges. Condensation particle counter. So this brings in those ultrafines that are too small to see, and it uses some kind of solvent reservoir. So we use isopropyl alcohol. And those particles absorb some of that alcohol, and they literally swell like a sponge. They go through a condenser chamber where the condensation happens, and those particles grow. They get big enough that then we can collimate them in through the laser beam, and now they're big enough to be seen. So they get focused through the optics, and the photodetector is going to see flashes of light. It counts those as electrical pulses. So that's kind of a simplistic version of how those things work. Back to sizes. Here's the chart of the different size particles. And I'm going to show this because in a minute I'll show you which instruments cover which sizes. There's some overlap. But there's a wide range in things like welding fume, some ash, some smoke. There's a wide range. So our health hazard issues is that we spirable and smaller, that 4 micron and smaller is what we're worried about for health. So stuff a lot bigger, yeah, we may be interested in steam if it's not getting deep in our lungs. There may be some metrics around that, but most of the stuff is for ocean exposures based on 4 micron respirable. So this is that same scale, but now we list the different type of instruments and what size range they can measure. So there's some overlap. We're looking at the top 3, and the condensation particle counter, C, that goes down to 0.01. So that's 0.01 microns. That's the same as 10 nanometers. So the P-Trak roughly goes to 20 nanometers, up to about 1 micron. And so there's some overlap with the photometer. It sees from 0.1 micron up to about 10, 15 microns. And then the optical particle counter looks at from about 0.3 microns up to 25 microns. So there's some overlap, but there's some differences. The real difference gets in the concentration. So photometer can go, the dust track can go from 0.001 milligrams per cubic meter up to 150 for the DRX and up to 400 milligrams per cubic meter for the regular dust track 2. So that's high concentration, that's heavy aerosol. Those levels are going to just overwhelm an optical particle counter. So in OPC, think of a clean room. You're measuring, in the clean room, how many particles of a certain size. So you're 0 to 200,000 particles per cubic centimeter, and then a condensation particle counter is 0 to 500 particles per cubic centimeter. Okay, so how do they work? So that was the little overview. Knowing how they work, you really have to understand kind of the basics of aerosol physics. So again, this is 5th grade version. I work with plenty of people that are PhD level, so there's some questions I'm not going to be able to answer, and I can get you in touch with those people if you need to. But really, there's different properties that affect how the aerosol is measured. Okay, so there's books that have been written on this. There's papers and journals all the time. There's ongoing research being published all the time of the effects of aerosols, the behavior of aerosols, and how to measure aerosols with different instruments. So there's a lot of information out there, and it really comes down to that these characteristics are important. That changes the way they're measured. Size is important for health effects. Size also affects how it's measured. The shape of the aerosol. They're not all spheres. So if it's a long fiber type thing, it's going to be counted differently than a ball. And so we're looking at average diameter as far as what sphere would fit around that particle. And then density. We're going to calculate how much they weigh based on how dense is that. So there's a lot of properties, as well as properties of how the light bounces off it. Color can affect it. A white aerosol versus a black aerosol. Will that be different? Will be measured differently coming through the instrument? Sometimes they will, sometimes they won't. So we're going to calculate mass from the known density of that calibration aerosol, and we'll talk about that in a minute. So as the aerosol is airborne, floating in the air, all the light coming through that is affected by the aerosol. So at sunset time, if there's a lot of smoke, and if we had forest fires earlier this year, we couldn't see the sunsets. It just got gray. When after a rain, there's a rainbow. There's light scattering through those water droplets, causing the diffraction of light, and it's causing a rainbow. So aerosols do different things to light. As the light passes through the aerosol, it's going to be affected by those properties of the aerosols. And so now here we look at the photometer. We saw this earlier. So a closer look. Aerosol comes in up on top. Some of it gets cleaned to go through a HEPA filter to keep a sheath that carries the clean air, basically carries the dirty air through the middle, so dirty air doesn't wander around and contaminate the optics. The laser beam sends out light, and the photodetector is going to see this scattering of light, this flash, or this fog. So there's a difference between what a particle counter sees and what a photometer sees. So the particle counter is really like counting drops of rain or snowflakes. So the optical particle counter, the condensation particle counter, anything particle counter, I think of it as low concentration, so less, a cleaner area. And so you're sitting in your car in the parking lot, there's a light rain, you can count the number of drops hitting the window at a level. It starts to rain really hard, you can't keep up. So higher concentrations in optical particle counters is not the best way to go. So the optical particle counters, condensation particle counters, they're counting the snowflakes, the drops of rain. It's going to work at certain sizes. We're going to keep up for a while, but eventually it gets, if you're driving too fast, there's just no way. So that's where the photometer takes over. So photometric light scattering, instead of counting particles, think of it as the photometer is measuring fog. So it's almost like it's zoomed back. It doesn't look at each individual particle. It looks at the fog. So how bright is that fog? How thick is the fog? You're driving at night and there's fog and the headlights are coming at you. You can kind of judge how far the car is away by, or how thick the fog is by how dim the lights are. So a photometer would see that, oh, brighter fog is thicker, heavier, and it's going to calibrate it back to, okay, when my calibration aerosol was this bright, here's how much it weighed. So it all comes back to that calibration aerosol. So, we calibrate to what's called a test aerosol, and it's an ISO 13023 A1 test dust or something like that. So it's nicknamed Arizona road dust, A1 test dust. And we know it's a known density. It has all this, the properties are known. It's a regular size distribution type stuff. So you know a lot about that, and that's standard for photometric instruments. But we're going to call that test dust a golf ball, okay? Because again, 5th grade level, this is about what I understand. So if I had a bunch of golf balls on the floor, so I came home, my kids were throwing golf balls over the house, pick up this bucket of golf balls. I can see how many are on the floor. That's about a bucket worth, or that's about 4 buckets worth, or that's about 10 buckets worth. And I know about how much a bucket of golf ball weighs. So if a photometer would see all this light scattered from all these golf balls laying on the ground and know, oh, there's about 4 buckets worth. That's kind of what the photometer does. It knows what a golf ball weighs. If I came home and they mixed golf balls and ping pong balls and tennis balls and baseballs and softballs and all kinds of other stuff, that bucket's going to weigh a different amount. Okay? Different properties, different aerosols. So a bucket of golf balls is going to be heavier than a bucket of ping pong balls. And if I don't tell the photometer the difference, it's going to say, here's your bucket. It weighs 10. Okay, well, 10 is what golf balls weigh. These are ping pong balls. It really only weighs 3. Okay, well, he's like, great. Well, you didn't tell me it's different. But, so the photometer sees a ping pong ball. It calculates mass based on what it thinks it weighs. And if we calibrate it to a golf ball, it's going to give us a mass based on that. So that's where the calibration aerosol comes into play. Your instrument's very precise. It's going to measure the same way every time. But the accuracy is based on how well that results measures your actual aerosol. So if your calibration aerosol is very similar to what you're measuring in the field, you're chopping up concrete, or you're driving down a dirt road in Arizona, and our test dust is Arizona road dust, your exposures are, your measurements are about exactly the same. Silica is going to be a little different. Wood smoke's going to be a little different. Welding fume's going to be a little different. They're different mixtures of balls. So we can develop a calibration factor to help that instrument better understand the properties of the aerosol. So the instrument just sees all these different sizes and shapes coming in. It measures the light scattering of those particles of group. It sees all these balls on the floor of the basement. It's going to calculate mass based on how many buckets of balls it's going to pick up. But it doesn't know, I'm jumping back and forth here, it doesn't know that way until we tell it. So to get that calibration factor, we can do a side-by-side measurement where we measure the mass. Again, don't throw the pumps away. Measure that mass on the filter. At the same time, you've run the dust track, and now you compare the dust track number to the gravimetric number. You take the gravity number on top, divided by the dust track number, and that's a calibration factor. So we've done some research, and other people have done research, and one guy came up with a cal factor for urban pollution, just outdoor air. Your cal factor for the dust track should be 0.38. So those are the ping pong balls. So the dust track's going to overestimate how much those balls weigh, because Arizona road dust is a different density, different properties than just outdoor ambient pollution, which is mainly combustion byproducts. So 0.38 will adjust that reading on the instrument to more closely align with that gravimetric result. So people come and ask, well, what is the cal factor for this? And I've been doing research, I've been pulling lists, I've been finding some for oil mist, I found some at 0.7, for forest fire smoke, I found some at 0.65. So the aerosol's going to be different. Your aerosol's going to be different than mine. Even if I had a list, it may not apply to what yours are. But that's how this instrument will get a better number, is if it's calibrated. And since we don't know what that aerosol is, that's why this instrument will never be that OSHA method to verify compliance for respirable silica or for hexavalent chrome and welding fume. It doesn't know what aerosol it's counting. It's here's the bucket of balls. You want to tell me how much a bucket of balls weighs? Here's how much the bucket of balls weighs. I don't know what kind of balls are in there. So if you've calibrated your aerosol to weighs this much, here's my mixture of ping pong balls, golf balls, tennis balls, here's how much it weighs, tell the instrument that, now it's going to be more accurate. So even without that accuracy, there's some stuff we can do that's good. So that gets into strengths and limitations. So that can be considered a limitation is, the dust track knows if it's calibrated to Arizona road dust, you measure Arizona road dust, it's right on. You measure something completely different, the numbers could be way off, but they're going to be that same amount off all the time. So that can be used still for data logging. We'll get to in a minute. Humidity changes things a little bit. And sometimes the optics can get contaminated, and then the instrument is not going to work. So that test aerosol, as we mentioned, it's very precise. That instrument responds the same way to that same light scattering every time. It's going to measure the same way every time. The closer your actual aerosol is to the calibration aerosol, the closer you're going to match your gravimetric results. So if you use a side-by-side gravimetric result, don't throw away the pumps. Pull a sample as you're running the dust track for a day, weigh the sample, the weight divided by what the dust track said it weighed, you'll get a custom K factor. And you can save those in the instrument. And I've heard from customers that had machining shops with oil cutting fluids, metal cutting fluids, this RPM, that RPM, this metal, that metal. They had different Cal factors for each of their instrument, each of their tools identified by using the dust track. So there's ways of doing that. So your aerosol is going to be different than mine, and customer A's aerosol is going to be different than customer B's, but that's how you want to do it if you want the actual number of what the exposure is. Humidity. These particles can be hygroscopic. It's a new word. I was saying hydroscopic before, which is incorrect. Hygro means it grows or it swells as it's exposed to humidity. So outdoors, humidity levels above 50%, there's a bunch of studies that show, yeah, a photometer is going to overestimate the mass because these particles get bigger. It sees softballs now instead of golf balls. It says, whoa, those are a lot heavier. So your reading is going to be elevated in humid conditions. So if you're doing long-term monitoring, especially outside, there's inlet conditions that can be added that will dry out that aerosol if you want to dry it down to 30%, 50% or something like that to normalize the weight. So when you do gravimetric sampling, there's humidity conditioning involved too. So the lab that's going to give you those samples, they pre-weigh those filters in a humidity conditioned chamber for 24 hours and let the humidity balance out. And they weigh them, they send them to you, and you take them to the field and sample them. It might be dry in Arizona, or it might be moist up in Seattle, and so that filter paper will collect the aerosol and will collect moisture in the air. So you'll bring it back to the lab. The lab will, again, let it normalize for 24 hours in that humidity chamber at that same temp, that same humidity it started. So it normalizes. So extra moisture will dry out. Extra, if it's too light, it'll come back. So we do that with sampling data anyway. So conditioning for humidity is done with sample data as well as gravimetric data. We just have an extra option there, an instrument, a tool added to the instrument to help do that. The contamination, really high concentrations of aerosol inside those chambers can get kind of plugged up. So we'll address this by zeroing the instrument every time we use it. We go out every morning and we put a zero filter on or a HEPA filter. Basically tell the instrument, hey, when it should be completely dark right now, there's no light being scattered because I have a filter on it and there's no dust coming in. So anything that's contaminated the optics that's sending some signal right now, just ignore that part and just look at stuff that's above that when I take the filter off. So that's how we address optics contamination. And then, dust track and some other manufacturers have that sheath air, so it's clean air going in, carrying the dusty, dirty air down the middle of like a clean carrier tube, basically. Another way to address that is that people, I'm out at a junkyard or a construction site, concerned about respirable silica. It's really dusty. Well, put an inlet conditioner on and put that PM4 impactor. You're going to cut out all the big stuff, and all you're going to see coming in then is the respirable, and that's what you want to measure anyway for your OSHA exposure levels. So doing an impactor up on front can help cut the big stuff out, help reduce some of the optical contamination. So yeah, it's calibrated to its own test dust. It can be affected by humidity. The optics can get contaminated. Those are the limitations. But the strengths, I think, way outweigh those. So you got real-time data. And even if you're not exactly the same as the number you gravimetric, you can see that log data on a graph going up and down. So we'll talk about that. You can set alarms. You can't set one with your sample pump. So, I mean, these strengths really, point 3 is, hey, what is the value of real-time data? So, if you're the incident commander, you get the phone call from the governor, how far downwind do we need to evacuate these people? What is that value of real-time data for you? If you have it, it's worth, it's gold, right? So if you have 10 dust tracks, you can field deploy in some enclosures on tripods, 6 blocks away, 10 blocks away, 12 blocks away. set up a perimeter, you can monitor that. You can collect data, and you can make a better decision. So having that data in real time can be valuable. And you may not even be calibrated to the right aerosol. It may not matter. We have aerosol above this level. This is we're half of the safe level at this point. We need to shelter in place. We get to the dangerous level, we need to evacuate, or vice versa. Whatever your decision making is going to be, you have data to do it. The data logging. This is my favorite part. So here's a guy working, and maybe we took a sample, some air samples last week or last month, and got the results back. And oh yeah, it was average was 0.52 milligrams per cubic meter. Great. Here's our photometer. We did it again with a AM510, and maybe our exposure limit's 1, so we're at 0.5. We're great. But then you look at the log data and it's like, well, how come you're high at 10 o'clock and at 3 o'clock? What's going on there? So just seeing the total for the day or the average for the day gives you one piece of information, but now seeing those trends, those peaks and valleys, you have more information where you can focus in on what activities are happening that causes the higher levels, and now you can focus your engineering resources, your control resources around those 2 peaks. Maybe you don't need whole ventilation for the whole shop. Maybe you only need to put a shot back in at the guy's workstation for these 2 times a day. So maybe you can be the hero and come in and offer some better advice because you have better data. Alarms. You can set an alarm to go off at a pre-selected level. So the alarm might tell people, hey, it's time to turn the fan on, or alarms are going on because the filters are clogged. So who knows? You can use it to stop work and adjust your controls, or you can use it to, time to put your respirator on, or we're sending dust across the parking lot. We got to stop what we're doing and spray some water down before the school district starts to complain down the street. So there's different ways of setting alarms up in these things, but you can't do that by collecting sample data on the filter because you don't get information in real time. Okay, so here's some case studies and applications. So there's just a couple, and I didn't want to bore you to death here. So first one shows an optical particle counter. That's an Aerosol 9000. These are really designed for clean room certification. So there's a couple different standards for clean room. There's this ISO standard. And I didn't have a copyrighted version or a non-copyrighted version of the chart I can put up here. So look up those standards if you're interested. If you've worked in quality and done clean room monitoring in pharmaceutical or semiconductor or even data centers, you'll be familiar with this. So there are different levels. It's not just zero. It's not just zero particles. There's maximum number of particles at different size bins to pass at clean room level 1, 2, 3, 4, 5, 10, whatever. So there's different particle sizes. So think optical particle counter, think clean room, okay, to give us a number of particles of different size. P-Trak, this ultrafine particle counter, a condensation particle counter. What we've had good success with people doing with these is kind of teach them to use them as a sniffer, and there really aren't metrics on what should be your air quality for particles per cc that the instrument measures. There really isn't anything established, but you sniff around and you find the areas that are higher than they should be. So here's an example of a hospital. So we have this in an application of, there's construction on the first floor, and on the second floor right above this, the people working on that floor were complaining of odors and headaches and scratchy throat type stuff. So facilities was involved, and the air ducts were separated off, and that's all done. The viscing was in place. So everything they thought they needed to do for construction-wise was being done. So they brought a consultant in, or the staff hygienist, or whatever, got a hold of a P-Trak, and so they're going to, everything else checks out. So let's check this. Let's check for ultrafines. So background outside, there's found 9,000 particles. So is that high or low? I don't really know. But, it is what it is, 9,000. And then he goes in, the supplier coming into the second floor is about 500. And most of the offices in the second floor is about 500. But then they come to the nurses area where the complaints are, and it's like 14,000. Well, there's that big difference. There's a big jump from 500 to 14,000. So now you have, okay, there's definitely something going on here. And they sniffed around that second floor and found an area. There's actually a joint on the floor, an expansion joint. Here's 150,000 particles coming through that joint. So they got a hold of the maintenance guys and got some duct tape for $5. They sealed up the joint and the problem went away. So they were a hero. For $5, they fixed it. They found it with an instrument that took them probably 30 minutes to run around. Get some real-time information, and they were getting data they could use instead of other stuff that wasn't measuring anything. So that's just one application of P-Trak. That's really the way we see a lot of people using these things. Perimeter monitoring. So here's dust track in an outdoor enclosure on a tripod. This customer actually has it on solar. So this is a picture I took of the actual customers in use outdoor. It's an open mine. And the other picture I've shown is just an illustration. This is not the same customer. I just grabbed this off the internet. It's a freebie from Google. I don't know where this even is. But I'm trying to show here we have a community, pretty large population center, and a pretty large open pit mining activity going around it. So if what this customer had done, or RS actually did, is the community was concerned about dust. So they actually have a line of dust tracks measuring not really the perimeter, but kind of along the whole ridge line where the community lives, and just seeing if they're, when they do a bunch of digging, when they do their blasting, are there raised aerosol levels? And these publishing this data for the community should see that there really isn't any change from their activities. So another way is, monitoring the perimeter of your operation. You can put weather sensors out here, wind direction, and dust, noise, whatever. And all of a sudden, if you start getting alarms from monitors 7 and 8, and their school is over here, and the daycare center is over here, it's like, let's hold on, the wind must have switched. Let's stop the trucks. Let's spray some more water down here so the dust doesn't keep traveling into town. So you can use that as early warning to try to set alarms, take some action, or you can just track data for community awareness. So oil and gas industry, oil refineries, they do this now. They have perimeter monitoring for gas and vapor. So that's required by certain things for emergency response. And the community calls like, oh, you're poisoning us. What's going on? So, well, here's the data. Same thing here. The community can get upset. You're stirring up too much dust. Like, oh, well, here's what the data says. You can take some samples there. So there's perimeter monitoring. And my last example, this is the example on the return on investment. So this, one of our channel partners told us about this, and this is completely made up data. I don't have their actual data, but it was a Foundry. They did a large investment. I don't know how much, but to me, large, I think $1 million. That'd be a lot of money. So think of doing a large investment in engineering controls, ventilation to protect for silica, metal fume, whatever else they're going on. So they did all these controls. They did some follow-up sampling, and one person came in really high for silica. And I don't know if I was the CEO or the president. I'm like, I just spent $1 million, and someone's still overexposed. What's going on? I mean, what we need to do. So they got, I don't know if the hygienist went back in, or if they got a consultant, but someone came in and used real-time dust monitor. So they used the dust track, they used the photometer. And I just made this data up, but I'm just thinking by what I heard, it was something like this. It was pretty low. The engineering controls work. They take a lunch break. It drops down almost nothing. Pretty low. And then at the end of the day, it just went through the roof. And that was high enough to put them overexposed for the whole day. So he went back in and talked to him and says, hey, what's going on at 4 o'clock? Well, we clean up our workstations. But at the end of the day, well, how do you do that? Well, they took out these air hoses and they blew the stuff around. So they're making this cloud of dust, cleaning stuff up. And so he was the hero. He said, okay, we got to stop doing it that way. Let's get a better tool. Let's get a vacuum. Let's get a little shop vac with a HEPA filter on it. Let's suck up all the dust instead of just blowing it around the room. So here, using real-time data, I was able to focus resources on a pretty cheap fix instead of changing again the ventilation for the whole area, which is very expensive, and they address the situation. So that's a way where real-time data showed a pretty good return on investment, because $50 or $500 HEPA vac shop vac versus another $1 million for changing the ventilation system or whatever the big numbers may be. So something to consider for future. These nanoparticles, we looked on the left end of those scales of the size range. There's a lot of nanoparticles out there. Ultrafines, these are combustion byproducts, small end rolling fume type stuff. If you were to measure them, there's not a lot of mass there, but there's a lot of them in numbers. There's very, very high numbers. So this is what the scientists are concerned about for nanoparticles and engineering nanoparticles. So they're looking at, maybe mass isn't the right number when the stuff gets so small. Maybe the number of particles, or even surface area, there's a whole different way of measuring the surface area. Maybe that's a better number for some of these things. So what are we going to see in the future? Will we see a number in the future that says you have to use a P-Trak or something like a condensation particle counter and make sure your indoor air is not over X number of particles per square cubic centimeter. I don't know. Maybe we'll see that or not. There was one regulation. The Switzerland is kind of like the California and the U.S. California implements tighter air regulation, and the rest of the country follows later on. Switzerland has issued a law. This is for diesel particulate monitoring for fixed sources like the big generators and off-road trucks and mining. So when they're digging tunnels, there's a filter on there, and they have a regulation now that you have to test the filter twice a year and make sure you're not spewing out more than 250,000 particles per cubic centimeter past that filter. So if the filter's working, it's clean. There's probably 400. There's probably cleaner than in a room. If it's not working, there's going to be 40 million. So it's yes or no, but they have actually a number, and you use a condensation particle counter. So TSI has an instrument that's modified. It's a condensation particle counter that cuts out the vapors and stuff, and it does that. So that's one that I know of. Will that come to regular cars? Will that come to occupation? I don't know. We'll see what the future brings. For now, I just spent some time helping you understand how photometric instruments work, some of the strengths and limitations. So if you know the limitations, you can change your expectations. If you know the strengths, you can probably use them for different ways than you thought of. And make those real strengths are, what's that value of real-time information from the log data? The stuff you can see from logging the data can really help make some better decisions. Showed you a few case studies, and that one case study had that really good return on investment where the person was a hero and found, if we stop blowing the stuff around at the end of the day and use a shot vac to suck it up, we can reduce that exposure. So that's time for question and answers. Tom, I guess you had some questions emailed in before we started, or give any others?
Yeah, we had a few questions come in. One was, I guess one of the first ones, you were mentioning some of the EPA standards earlier. What's the EPA's view on this measuring technique versus the other federal reference methods?
Yeah, so there's almost like 5 levels. I mean, there are still places where the EPA wants a filter collected, but they're recognizing, and we put out a new environmental dust track that's really aimed at this market. It's other method 34 or something like that EPA has, where they've said you can use real-time photometric measurements as a good enough measurement indicator for your air pollution. So especially like a construction site, it's quick and easy. You set it up and run it. It's not the same as the city of Minneapolis is going to have their official monitoring station at the airport. What's their long-term regional air pollution levels? But the quick and easy for companies to set up, it does say specifically in there, instruments like the dust track work really well. So I didn't have that in my presentation. I can get that to you if it's something you want to share with your team. I can pull those 2 slides out of that presentation, just kind of add it on the mind here for later.
Yeah, if that'd be available. Yeah, that'd be helpful.
Yeah, so it was other test method 34 EPA, and I forget which section EPA that's under, but I have like a 2-page slide set on that helps explain it.
Okay. There's another question about humidity. You mentioned that humidity can affect measurement. I mean, how much of a variation is there, and is there really anything you can do about that?
Yeah, so if you're measuring outside, if it's always humid, in Hawaii it never changes. So you're probably okay. You're just going to do a cal factor and adjust it, and you're probably good to go. But somewhere like out east, I know we had some customers using their dust tracks. It was like bridge construction and pretty sensitive levels, sensitive population, high density population, and the numbers, they get alarms going off in the summer when the humidity got up there. So for them, it was pretty sensitive. So using that heated inlet is the accessory we added in line to do our outdoor monitoring. The new environmental dust track has, easy to swap the heated inlet in line, so that will condition it. The testing I've done and seen is about a 30% difference in the reading. So without the heated inlet, or with the heated inlet on, your numbers drop by about 30%. Now, I've looked for studies, and I've seen some other people say, yeah, it will drop. I haven't seen anyone publish this aerosol, this percent. It's going to depend on what it is. Some aerosols will swell more than others, but I haven't seen about a 30% difference in some of the stuff we've tested. So that may be enough to put you over that alarm level if you have community action levels or something like that. So you want to help make sure you're not, your alarm is real in all times of the year. So we're recommending for outdoor monitoring, if humidities can vary up to about 50%, have the heated inlet down there so you can normalize, throughout the whole year.
Okay. Another question kind of along those lines of how big of a difference can there be from various aerosols from the Arizona Cal? Are most aerosols in the plus or minus 20% range mass, or could it be bigger than that?
Oh, yeah, that's a good question. So I'm trying to put an app note together on stuff I can find from other research. So I'm digging into that, and so some for the urban pollution, just urban combustion byproducts is 0.38. So that's a pretty, from 1 down to 0.38. That's a pretty big difference. So basically, that's it's you're probably about 3 times higher than if you're not using that Cal factor, your numbers are probably 3 times higher than they should be. I saw other ones in like 0.7, 0.6, 0.5. Wood smoke was like at 0.6. So they're all in there, and I haven't come across stuff that's heavier yet, of like the 1.2, 1.3. So I'm trying to find out if I'm thinking metals would be a higher density than dust, than dirt, but I'm not seeing the higher ones. And it's, part of it, I'd like to go back to grad school and do research projects on this. So, you're meeting, anyone out there, you ever run across some grad students that need a thesis project, have them explore, sell them a dust track and say, hey, go to work and get some Cal factors developed and figure out what it is for all these different things. I've been seeing from like 0.38 is the lowest I've seen so far for that urban pollution. I've seen a lot around 0.6, 0.7, 0.8 in that area. So I'm trying to get an app note out by the end of the year here on that. They'll help summarize so we know for silica, here's about what it is. The point being, you shouldn't set yours at that, but if you do your own custom Cal factor, you can compare it. Say, oh yeah, mine's close to that, so I must be right. It gives you a basis of comparison.
Okay, good to know. I want to ask if there's a point that, or I guess if there's some measurements where you want to take a gravimetric sample as well as the real-time measurement. Are there any situations where you'd want to do that?
Yeah, so if you don't know what is in the dust, and if you send it in, the filter into the lab, can have it analyzed, and they have pretty expensive machines, gas chromatograph and stuff that can break down and give you what metals are in this sample, what percentage of what metals. So that may be important if you're doing a metal scan. You don't know what is in the air. So there's reasons for you have to kind of tell them, look for either organics or look for metals or look for this or that. It's not as easy as on the TV shows, but you definitely want to do some samples there. And then OSHA still, if your photometer doesn't know what your aerosol is, so it might be overestimating the number, it might be underestimating what your actual exposure is. So doing that side by side, if you do a gravimetric sample, like run it for a whole shift with your dust track, with an air sample right next to it, collecting the sample, and if you do a couple of those, now you have some data you can compare. And there's an easy formula. It's just that gravity number divided by the dust track number, and that's your Cal factor. So that if you put that number into your dust track, that should change your number from golf balls to whatever your bucket of aerosol is. So since that aerosol could change throughout the course of the day, OSHA really won't recognize, if you have a photometer reading, it's not the same as compliance monitoring because you haven't actually measured the weight of that contaminant. So until the metrics are still based on mass of lead or mass of hexavalent chrome or mass of silica. So there still is reason for taking those samples and verifying. So I suggest people, if you've had consultants come through or you've done it yourself and you verify, our workers are safe, we're below the level of concern, well, great. Put a dust track with it, and now here's your dust track number. And now, as long as that dust track number doesn't go up, you should be safe. In fact, you start seeing the dust track number change over time, and just maybe it's a spot check every day or every week, all of a sudden it's doubled. Like, something's going on. We should probably pull some air samples again and make sure that people are exposed. So usually it's kind of a measure of control.
Okay. Another application question. Could the dust track be used to quantify the emissions from an industrial baghouse dust filter?
I'm not sure. So if there is the air comes out of the dust track too. So I know there's a way to plug a your aerosol comes into the top of the dust track and goes out the bottom of the dust track. So you've had both tubes in the sampling duct. If that sample's at a different pressure, you can normalize the pressure in the dust track doing that. As far as the levels, I mean, if the levels are within 0 to 150 milligrams per cubic meter, yes, the dust track will read that. And if it's size 0.1 micron up to 10 or 15 microns, yes, the dust track will see that. So I guess will it get the proper sample into the dust track? That's what I don't know. And if it's air moving through a duct or through a bag filter, that's just how are we sucking it in? So that the dust track pulls up 3 liters a minute. So if you put that sample tube in that line, in that duct, I don't know if it's there's probably a way to figure out is it pulling enough air to get a representative sample out of that ductwork. That makes sense.
Well, so if you use,
it's most likely going to see it, but will it draw an adequate sample out of that moving airstream? That's what I don't know.
yeah, I guess if you use like an isokinetic sample probe, that may be able to draw the sample, and then it would work all right.
Exactly, yeah, because those have to be pointed right upstream and it's really the same flow rate. So if you have the same flow as your airstream is moving, then you're pulling a representative sample instead of pulling. If you suck too much, it's like a vacuum sucking stuff in from around it. So yeah, you can. An isokinetic is kind of, I haven't done it, but the dust track's set up to do that by having the import and the output. So you can normalize that pressure and do that with the dust track.
Okay.
But it sounds like particle size range and density range, and as far as concentration, it's probably within that range. It's just the challenge of getting that isokinetic sample collected.
Very good. Another OSHA-related question: is there any way to standardize OSHA methods, like cassette kits, when using air pump monitoring? I don't know if that's beyond our purview what we get OSHA to standardize with, but
I don't know. It's so there's OSHA methods for analytical, and then there's NIOSH methods for analytical. So there are a lot of published things as far as you're going to take an air sample and measure it for a certain constituent. I mean, there's guidelines on how the analytical method works. So that's pretty well understood. Will OSHA come up with something to use a direct read instrument? That's a good question. I guess that'd be interesting to see. If that's the direction the question is going. But for yourself doing it, if you're documenting, probably you want to have documented that you've taken gravimetric samples, document that yes, we're at this level of exposure, we're below the level of permissible exposure level. And now if you add to that your direct reading instrument information was another layer of information ongoing, I think OSHA would come in and say, oh yeah, that's great. You know you're in control because you keep looking at it every week with the dust track. Every month you verify. Instead of taking a sample once a year and measuring it, you're doing the check every week. So I've probably thrown more at the question there than I hope to answer what they wanted, but I don't know. Does that answer it?
hopefully so. So we're kind of at the end of our questions here, and we're closing on the hour, so may need to wrap it up. If anybody has,
there's my contact info.
Perfect.
People just give me a call or send me an email. If I didn't answer that question well enough, maybe I just didn't understand it right, but give me a little more info. I'll dig into it a little more with you, and we can talk and see what we come up with.
Perfect. Appreciate it.
Yeah,
and again,
just some new ideas of different ways that this instrument work. That stuff. I kind of want to jump back out in the field and use these things. It'd be fun to do. But, I want to be the hero and find the problem and make this big solution with a real-time instrument. So.
That's it. Absolutely. All right. Well, thanks so much for doing this for us, Scott. If anybody else has any questions at all, you can email Scott, or you can also email us at Rayco. If you have questions about the presentation as well, you can reach me at tom@rayco.com. And I'm getting played off here like Yemi or something. Interesting. Anyway, thanks everybody for joining us. Look for our invitation. We'll be doing another webinar next month, and hopefully we'll see you there. So thanks a lot, and everybody have a great rest.